So the soundings for me are, it's the main tool I use for understanding what the day is going to be. So you can look at them 2 days in advance. They don't have a real long, there's not a real long forecast period on the forecast soundings, but it's it's the day before or that morning what I look at to see what I'm going to expect for that day. So, how many people are familiar with soundings, with the SKU-T log B? So, how many people are comfortable reading them? Okay. A lot of this. So, okay, well hopefully by the end of this, you'll be even more confused. No, you'll be able to.
Russell, just a quick question. The thing that I think I stumble on most when trying to do this is I don't know exactly where on the internet to go to get them. And when I get to a site, it's like there's 25 choices. There's all these different, abbreviations and stuff, and it's like which one do I choose? On some of them it gets real complex in terms of SPOP, this, all this.
At the very end here, I'll have the.
Okay. All right.
And like for Minden, you can go to our website. Soaring ND website, go to the weather page, and it has the forecast sounding. So right there. Okay, so a sounding is simply a bunch of information. When used to, there were just measurements. They'd send a balloon up at 0 and 12 Zulu everywhere around the world at the same time, and plot the sounding. Now they do forecast models, computer models, so that you can get them throughout the day, and they are pretty accurate. So it is just information about the temperature, the dew point, the wind direction, and the wind speed. And it's plotted on this really complicated, confusing diagram, just what gives most people problem is just understanding what all those lines are. So I'm going to break it down step by step, and hopefully we'll start making some sense. So what we're going to go over is, why do we want to use these in the first place? What can we learn from them? Then we're going to start talking about the properties of the atmosphere that lead to the SKU-T diagram, SKU-T log P diagram, and then we're going to go over a bunch of sample soundings. So, why use soundings? Because they're really, really useful for understanding atmospheric stability, understanding when the trigger time or temperature is going to be for thermals, knowing how high the thermals are going to go, understanding if the thermals are going to stick together, if they're going to get blown apart by the wind, whether we're going to have clouds or not. If we do have clouds, he's not here today.
No.
I'm just marking him off completely.
So that's one wrong.
That's only one run? Okay.
So people will start on the second one.
So I'll sit here, I'm going to hand that back to Monson here, and have him do another. Okay, so it was a presence of cumulus cloud base and tops, so if there's going to be thunderstorms, you're going to have cirrus clouds, which can work against the creation of thermals. Or if there's going to be wave, and if there's wave, there's going to be lenticular clouds, and of course, knowing what your headwinds and tailwinds are going to be how they affect your glide slope management and planning. So you can get all that from that one little diagram. So, I'll talk a little bit about the atmosphere. One of the main things that you need to understand is that changes in pressure cause changes in temperature. So anybody who's ever used a bicycle pump and felt it after they pumped up a tire, the bicycle pump gets warm because you're compressing the air. When the pressure increases, the temperature increases. Conversely, if you've ever used a spray can, you know when you spray something out of a spray can, the pressure in the can is going down and the can gets cooler. So that's just these are two examples of adiabatic. It's called adiabatic warming and cooling. And the same thing happens in the atmosphere. If you take a chunk of air here and you move it up because the pressure is decreasing as you go up, it acts like that spray can and it gets cooler. You bring it back down, it warms back up. For no other reason than because of the change in pressure. Okay. So if I were to plot this on a diagram, what I've done here is the temperature is along the horizontal axis and the pressure in millibars is on the vertical axis, but what I've done is we've flipped the axis, the vertical axis. So instead of going from low pressure at the bottom to high pressure at the top like you normally do, you've done it upside down. The reason that is because that way it corresponds with what happens in the atmosphere better. At low altitude you got the high pressure, high altitude you got the low pressure. So this is just a plot. If I took a chunk of air at 20 degrees Celsius at sea level, which is about 1,000 millibars, and I just decrease the pressure either by raising it up or just by decreasing the pressure, putting a vacuum on it, then it would change with temperature along that line. So it's just an empirical, it can also be calculated, this could be an empirical measurement. So by the time I got that thing down to 500 millibars, it would be about negative 32 degrees. Started out at 20 Celsius, half the pressure, decreased to negative 32 degrees. Okay. So that would be called, that is an adiabat. That is a dry adiabat. Okay. The reason it's called dry is because air behaves differently because it has moisture in it, or more precisely when moisture comes out of it. So I know if I had a pan of water and I want to turn liquid water into water vapor, I have to add heat to it. Okay? So that heat heats up the water eventually turns into steam. Excuse me, it does not turn into steam. It turns into water vapor. Big difference. So it turns into water vapor. It dissolves in the air basically. That heat that I used to get that water to do that is still part of the water vapor. It is still there. When that water vapor then condenses back out for some reason, if I cool that air back down a little bit so that the water vapor starts to condense out, it actually gives off some of that heat as it condenses. Because of that, if the air is saturated and I decrease the pressure so it cools off further, it's not going to cool off as fast as if it was dry. So it's not going to follow that dry adiabatic curve. It's going to follow a new curve, which we call the wet adiabatic. So the blue one is how fast it cools off if it's not saturated. The orange one, if it's saturated. Okay. Now, to make those lines straighter, makes things easier to read, I changed my axis there, my vertical axis, to a log axis. So much closer together at the bottom, get further apart as you go to the top. It's just a logarithmic scale. The nice thing about doing that is the pressure in the atmosphere goes logarithmically with altitude. So I can now put, instead of having to read off millibars, I have thousands of feet here that I can read off in a linear scale. So by changing the pressure to a log P, log pressure scale, I've got a linear altitude scale. So now another way to put this is if I took a chunk of air at 20 degrees Celsius, took it up to 18,000 feet, then it would have decreased its temperature to negative 33. If I took a saturated chunk of air, it was already at 100% humidity. So as soon as I start decreasing the temperature, it's going to start condensing out water. If I raise it up to 18,000 feet, which is 500 millibars, it's only at negative 10 degrees. So it didn't cool off nearly as much. Right?
Is that 2 degrees centigrade 1,000? Is that right?
Yeah, roughly.
And anything below 0 can't hold moisture, because that's a freezing point of water.
Yeah, no, it can hold moisture.
It can hold moisture.
Oh yeah.
It's counterintuitive, but it's not the same when it's dissolved in air.
Yeah.
Okay.
If it was liquid, it will be solid. Excuse me. If it is not vapor, then it would turn to solid, not liquid. But you can still have water vapor in the air, even though it's below freezing. Okay. Now to get right now, it's very spread out this way. I'd much rather have the information closer in. The way to do that, because this part of the graph and this part of the graph don't get used very much or at all. So I want this part of the graph. So I'm going to take this part and just go skew it over. Okay, that's where the skew t comes in. Skew t log p, or log p skew t.
And
So
that's why those other lines then are crooked on there.
So I've skewed it over. So now I've got a skew t log p diagram. So if I go ahead and fill in the corners here, now I lop off the parts that I don't want and do a different color. This is the basis of the skew t log p diagram. Okay, so it still has the temperature lines are in red here. So if I was at it's called the sea level at 20 degrees, and I want to plot 20 degrees at 20,000 feet, that would be that point there. It used to go straight up, now it's skewed over. So this is a constant temperature line. That's a constant temperature line. Okay? So from here I can start plotting stuff. I could just plot some data on there. If I sent a balloon up, took some pressure, temperature and dew point readings, I could plot them like that. Now, the real usefulness of these diagrams is to show what the air is going to do when it changes altitude. So now I take that dry adiabat I had earlier and I plot it on here. And it looks like that. So again, I know if I took some 20-degree air at sea level, raised it up to 18,000 feet, it's about negative 33 degrees. Okay. Now I decided to plot, well, what if I did it for 30, 40, 10? So I put a bunch of them on there. So that now I can say, well, if I had some air that was at 15 degrees, well, it's going to follow basically along there. So it just gives me a guide to look at what a parcel of air would do if I change its altitude.
So it's the dry 80 of that, just put several times
Yeah.
so that you can follow
I
it
could
easily.
agree. I could agree.
So that I can kind of guess. I know this is going to be right in between those two. What do you think of that? Okay. Now let's throw a wet adiabat on there. So the blue lines were the dry adiabats. Now the orange line is that wet adiabat that we looked at earlier.
That's the 100% saturated, right?
Yeah, the wet adiabat is always assumed to me that is how, if it was 100% saturated here, this is how it would behave as it goes up. Okay.
Second time around.
Yeah, we're putting the list around twice because,
Okay, I just put an A on mine.
yeah, just mark it off if you're not going to go. Okay, so then I throw some more wet adiabats on there. And this is where it starts getting confusing.
It's a busy chart.
It's a very busy chart. That's why I tried to step through it slowly so you can see that, oh, it kind of makes sense if you don't look at everything at once. Okay, so now we have lines everywhere, but we know the blue lines are dry adiabats, the orange lines are wet adiabats, the red lines are temperature, the black lines are pressure, and the blue horizontal lines are altitude. Simple. We haven't even put any data on there yet. Okay, but I'm joking. But does it make more sense? Does it make some sense now? Yeah.
Yeah.
Give me a yeah. Okay. Otherwise, I'm going to go back and go through it again and again. Okay, I've got one more line to throw in there. So we've talked about how the temperature changes with altitude, with pressure, whether it's saturated or unsaturated. Now we want to talk about how does the dew point change with changes in pressure. Now the technical term for that is the mixing ratio. For a constant mixing ratio, that's a constant dew point. So we'll consider the mixing ratio lines the dew points lapse rate lines. So if I took some air here that had a dew point of -8 degrees, then it would change, as they brought it up, the dew point would change along this line. So if it had a dew point of -8 here, by the time I brought it up to 20,000 feet, it would have a dew point of -17. -10, -20, -17. Kind of. Okay? It's different looking at it with the skew T in there. That takes some getting used to. But you always just, this point right here, halfway between 10 and 20, so that's 15 degrees. This point right here, 0 degrees. Here, 8 degrees. Getting that? So, if I took a point straight up, that's 0 degrees, -10, -20, -30. So, okay. So now we've got almost everything that goes on this graph. So there's my mixing ratio lines for a lot of different temperatures.
Why do they, is this just because you built this yourself, or why are they, gray lines are not equally spaced? Is that how they actually appear on the chart?
Yeah, because they're, yeah.
Okay, we'll talk about that later. In this area, it's like every 10th, and then it goes to a different value because as you go to the lower temperatures, look what happens here to the dry adiabat and the wet adiabat. At low temperatures, they come together because the air can hold so little moisture at those temperatures that when it gives up the moisture, it doesn't make any difference.
It's not giving off any heat.
It's not giving off any heat. There's no latent heat in there because there's so little moisture in there. Down here, there's a huge difference between the temperatures, which means how much. Here, say if we had, let's follow this one here. The temperature down here, there's you can think of it as holding that much moisture. That'll make a huge difference in temperatures. I'm just going to let you sit with that for a minute. Okay. One more piece of information, which is the wind. So the wind on these diagrams goes over here on the right. The blue line is just the magnitude of the wind. So I can look here and say the wind at the surface is practically 0. At 10,000 feet, it says 0, 50, 100. So we've probably got about 20 knots, 15 knots, 20 knots up here, 15 knots there, and on up to about 45 knots up here.
So it matches the barbs.
this is the wind direction from here to here. So this would be a southwest wind. This would be an almost west wind. This is a northwest wind. The barbs, okay, that looks like a flag. It's not. That's the 1 1/2 a barb, in 5 knots. Let's look at this one. You've got a barb and a 1/2 a barb, so that's 15. 2 barbs, 20. A barb and a 1/2 a barb, a flag and a 1/2 a barb, that's 55. So every flag is 50, every barb, full barb is 10, and every 1/2 barb is 5. Or, I could show it like that. Oh, I'm sorry, it was on the left side of the diagram there. I knew I had this one. Okay. Now, we're going to actually use it a little bit. Now, what I'm going to do here is I'm just taking one parcel of air and looking what's called a parcel trajectory. In other words, how the parcel will change with altitude. If I take a parcel of air that's 26 degrees, 25 degrees? No?
Oh, yeah.
Yeah, halfway between 20 and 30. And the dew point of, I don't know, about 5? Minus 5, sorry, thank you. Okay, so as I decrease the pressure, I raise in altitude, bring it up in altitude, it follows the dry adiabat, so we know it goes up to there. Okay. The dew point follows the gray line, goes up to there. Now what happens here is that the dew point and the temperature are the same. That's the definition of saturated, right? So from there, the temperature is going to follow parallel to one of these orange lines. So it's now going to follow up saturated. And if it's saturated, the dew point and the temperature are going to be the same all the way up from there. So if I took this parcel of air up, it would do that. Does that make sense? And there's water coming out of this. So that means there's either going to be a cloud or rain or snow or something forming once this happens. Moisture is leaving the air. Okay. So if I took this parcel of air up to here, and then I started pushing it back down, it's not going to go down along this line unless the water is evaporating out just as fast as it condensed out, which it never does. So let's say rain fell and just completely removed the moisture from the picture. Now it's going to come down along this line, right? Because it's going to be a dry adiabatic heating. So I pushed the air up along here, went there, and came back down here. So that's why we have deserts behind mountains. Downwind of mountains. The air gets pushed up the side of the mountain. Let's say the mountain is at 20,000 feet. This is a big mountain. Goes up to 20,000 feet, drops its moisture on that side of the mountain, or excuse me, that side of the mountain, the west side of it. Now it comes back down the back side, and it's hotter and drier by the time it gets down here, just because it gave up the moisture. Okay. Now, we're going to look at the actual data. So that from before, the one I just showed was just a parcel, was one data point basically at the ground level, and we saw how it changed. Now, this is data from the entire atmosphere. So this was measured or computed about how the temperature and the dew point were distributed in the atmosphere. So I know now. Well, first, there's a few things that I would use to describe this sounding. From here to here, it's adiabatic. It's dry adiabatic. Okay, that means if it gets a little warmer here at the surface because it was a parking lot or something, then that air is going to keep going up because it's always going to be slightly warmer than the air around it. So if I have an adiabatic atmosphere, that means any spot warming is going to cause lift to go until it's no longer adiabatic, which would stop that right there. So about 17,000 feet here is where this inversion is. And one of the things to note, it's not actually an inversion. The temperature doesn't actually decrease with altitude. It just stops decreasing adiabatically. So, you know, it's still cooler here than it is here. It's just not adiabatically cooler. So it's not a true inversion as in,
The air down at the bottom isn't dry, it's air. So it has some moisture in it, whatever it is.
yeah, it has a dew
So
point.
why is it following the adiabatic line? The dry adiabatic line?
No,
It's
'cause
got
the-
moisture in it.
Yeah, but it's not condensing out. The moisture only affects it when it condenses out, when it changes from vapor to either solid or liquid. That's when it releases its latent heat. Until it becomes 100% saturated and starts to give off that moisture in a solid or liquid form, it doesn't change the temperature check.
So it follows the dry.
Yeah. It's that change of state from vapor to something else that gives off the heat.
Now the adiabatic rate is the theoretical rate, and in this sounding, that's the line we're following. But will there be examples where it would follow a different line?
Yes.
And if so, why?
Yeah, let me get to that.
Okay.
I will explain that. I promise. Okay, so there's a lot more of these to come.
What are the blue numbers
From last
on the
year, I
right?
remember nothing from
What's
last.
that? Blue?
Thank you.
Those are temperatures.
But the temperature was down below.
Oh, I'm sorry. These are. I don't know what those numbers are.
Dew point.
Well, a little bit.
Yeah,
Well, that's the. Well, they're labeling the adiabats, so I don't. Oh, it looks. No, that's not right. I don't know. Okay, so there's this inversion at roughly 17,000 feet, which isn't really an inversion, but that is what we call, I mean, when a meteorologist talks about an inversion, this is what they're talking about. They're talking about it's cooling off faster, or slower than adiabatic. Okay, so thermals would go up to that and stop. Okay? Oops, back up. One more thing. When I'm looking at convection, I'm only looking at what, like we did in that previous slide, these 2 points, because that's the air that's going to heat up and start to rise. So from that, I can ignore everything up here. If I know that this is going to rise to here, I know that the dew point is going to follow this line here, and they're going to hit together here. Right? So that's where my cloud would start to form. That's where cloud base would be for cumulus. And then it would continue to go up along, parallel to one of the orange lines, and it would stop right there, because that's where it would no longer be warmer than the air around it. Okay?
And if the lines come together either close or touch, it just means that there's condensation going on at a level that's not caused by convection.
Yes.
So like a cirrus layer or something like that.
Exactly.
The blue line is the actual measured or computed
Dew point.
dew point.
Right.
But you said the dew point would continue on the.
A raised parcel.
Yeah.
Oh, okay.
Yeah,
Raised parcel.
Right.
Okay.
So it's this chunk of air that's rising up.
Yes. Okay.
So
Okay.
if I took this chunk of air and
Yeah.
forced it to go up, it would go on
Yes.
up along that line.
Okay. Okay.
So. Okay. Now, one of the things, get all done, great.
Actually, on that last point,
Yeah.
can I pile on? Does that mean then, if we're in a mountainous terrain, and the tops of the mountains are at the 700 millibar line, that you would be raising that parcel in the mountains versus the valley here, and then following that?
Not really.
Okay.
Kinda, maybe. It depends on what. I mean, say this was the sounding in the valley before the mountain, then this whole parcel would go, this whole thing would get moved up. So yes, there would be some places like here where it's closer together, more chance of having clouds. Okay, now imagine we were doing it the old-fashioned way with balloons. If I sent up a balloon and it happened to go through a chunk of blue sky, but half a mile away I sent one up and it happened to go through a cloud, they're going to get totally different readings, right? Because the fact that there's a cloud here means that it must have been a little bit warmer here to cause some convection. So, you know, if I send it up over a Walmart parking lot versus over an irrigated field, it'll make a difference. So, anytime you're looking at these, at either a measured or a forecast sounding, you've got to realize that there is a band of variation at the very bottom. It could be a little cooler or a little warmer than what they're stating. And that is why we get thermals. So, let's look at that previous one. If the air actually, in one location, follows the dotted line instead of the solid line, so it's a little cooler. Well, that air is cooler than the air around it. It's not going anywhere. Okay, so it's stuck. If that air is a little bit warmer than the air around it, well, now it's warmer, so it's going to climb. Because the atmosphere is adiabatic there, it's always going to be warmer than the air around it until it gets to here, at which point we get the cloud forming. Now it's going to follow the wet adiabat up to here, and now if it kept going, it would be cooler than the air around it, so it stops there. So the cloud base happens when the dew point and the temperature come together. The cloud top is where the temperature line and the actual temperature, the ambient temperature, come together.
Say that again.
So, right now, ignore everything except for this. Imagine a blue dot there and a red dot right here. If I just force those to go up, they would follow these lines till they saturated and then follow the purple line on up. Okay. Now, that's if I just forced them up. Well, the thing is that the temperature of the atmosphere is actually a little less than the temperature of this parcel. Therefore, I don't have to force it up. It's going on its own. And it's going to keep going up, cooling off, but cooling off slower than the air around it until I get here. At that point, the dew point and the temperature are the same because the dew point has followed this lapse rate. And again, it's the parcel at the ground. So the dew point and the temperature came together. Start to get condensation, so it's going to cool off slower. And it's so that now, if it kept going up any further than that, it would be cooler, to the left of the red line, which means it's not going to go there unless I force it. So it's just going to stop right there.
So, Russell, the purple line starts off following the dry adiabat line.
The purple line is a dry adiabat.
Yeah. And then once it gets to the horizontal black bar there, cloud base, it then starts following the wet adiabat.
Right.
That's the orange line, so it's parallel to the orange line.
Correct.
Okay.
Because it's saturated at that point, so
Yeah.
it's going to follow.
And actually, that purple line, Russell, is that you're looking at this on the closer Zulu that you have, and then the actual temperature, and that's the purple? That's where I get lost.
Say again?
So to build this scenario, in a practical sense, you come to the airport, you pull this chart to the closer Zulu time, that is your actual time, then you look at the temperature, the actual temperature, and that's how you come up with that line, the purple line?
No, I just know that there's going to be a few degrees variation. So,
How do you know that?
because there's always going to be variation.
Well, I know that, but is that based on actual temperature, that you look outside and said, oh, this was predicting
Because
20 and now it's
you know the
24 C?
parking lot is warmer than the lake.
Yeah, you know that the airport runways are always going to be warmer than
Warmer.
the crop circle. So it's just going to be some variation.
They call it a trigger temperature, is that right?
Yeah, not right, not quite.
Well, you can think about it that the sounding is representative of the atmosphere, sort of independent of what's going on at the surface. Okay, and then so you get the local variation in surface temperature due to the sun shining on it, so a parking lot gets hotter, so you get that then shifts that temperature near the ground.
The sounding is the average of everything because it's a computer model. It can't do parking lot by parking lot
Stop,
computation.
Starbucks.
So it's an average. So yeah, we just always got to assume that there's some variation, and that there's going to be some a part that's slightly warmer, and if the atmosphere is adiabatic, that's all it takes for it to start going up.
Russell, weren't we looking at the high temperature of the day too? Like the sounding was taken in the morning,
No.
you go to the high point, and you say maybe.
Yeah, you can do that, and that was more the technique when you only had for around here, the 4 a.m. sounding. Then you would use that with the predicted high temperature and get an idea how high the thermals were going to go. This is much more accurate than that because, number one, those soundings were taken at, locations like, for when I flew down in Hollister, we took the Oakland sounding. I mean, totally different. I don't even know, I don't know if there's there is a Reno sounding. They set up a balloon here. So we got something here. But this is way more accurate. And you'll see on some real soundings where it will have these little hooks here, where the red goes to the right a little bit, meaning that it's saying that the surface is going to be hotter and there's going to be a lot of instability where stuff's going to go up and down.
It's actually predicting that now.
So I think I follow everything except for blue dash line. What I'm thinking of is why isn't the temperature here rather than here?
Because this is the data, this is the dew point of the air at the surface. Okay? And it is that actual air that is going to be rising.
Like a box of surface air.
Right, if I took a box of surface air, decreased the pressure, then, and without decreasing the altitude, just I would start to suck a vacuum on it, then at a certain point, once it got down to 580 millibars, I would get condensation on the inside of the box.
So then what it gets confusing for me is then what is the rest of the blue
That's
line?
just the distribution
Yeah.
of the atmosphere.
That
Red-
altitude.
Red
Yeah.
and blue would be what you would measure if you sent a couple sensors up in the tow plane to go up to 15,000 feet. That's what the profile would show.
So if to go back to my balloon going through the blue sky versus balloon going through the cloud, if I sent the balloon up and it went through blue sky, it would measure this because it would be measuring what the atmosphere is like. If I sent the balloon and it happened to go through the cloud, then it's going through air that a few minutes ago was on the ground. So it's going to be measuring this.
And based on this, you can predict that there's going to be at 15,000 feet.
Okay, so I'm going to step through what soundings would look like for a given day. So, 6 o'clock in the morning, which I had never heard before. Then, there's a hook here on the temperature that goes to the left. It's radiation cooling. As overnight, the surface always cools down because it's radiating heat and it's not getting it back from the sun, so the surface cools off. That cools off the air around it, and so we get a big inversion first thing in the morning. It's going to be way colder down here than it is just a couple thousand feet up. Okay, so that air is not going anywhere. It's stuck there on the ground
Until it heats up, right?
until it heats up. So I've got this low level inversion from the radiant heating. I've got a chunk of adiabatic air here from 8,000 to 12,000 or so. It basically follows the dry adiabat. And that's just air that has been there since yesterday. Because most likely yesterday there were thermals going up to that altitude. And it's still make it still this that way. We've got a mid-level inversion here.
A horrible thermal day.
Huh?
Not a good thermal day.
There'll be thermals up to 12,000 feet. There'll be clouds. So we've got the mid-level inversion, and then we've got an upper-level inversion. So there's always an upper-level inversion where the atmosphere starts to go isothermal, the same temperature pretty much all the way up. Not quite, but pretty close. So that's always there. That's what always, and it can be here, it can be here, depending on how high it is, depends on how high the air can go, like for thunderstorms and stuff. So this is how I would, if I was going to describe the sounding, I would, can sound really technical, I'd say that there's a low level inversion, adiabatic lapse rate in the mid-level, a mid-level inversion, and then another upper level inversion. Okay. Now, get to 10 o'clock. Sun's come out, and we've got a little bit of heating. So what happens is, once that bottom part of the atmosphere starts to heat up, it starts to mix. Within a certain amount of time, the entire bottom 3,000 feet, 2,000 feet have now become adiabatic from all the up and down motion that's happened in that layer, in that mixing layer. Okay? So now we've got adiabatic up to 6,000 feet. Okay? That low level inversion is still capping the thermals though, so if we get some area that's a little bit warmer, it'll only go up to there.
What's the, define an inversion? I hear the word and I can see the line, but what is that saying?
It's saying that the temperature is not cooling off adiabatically. It's cooling
That's
off.
all it's doing.
It's cooling off less than adiabatically. And it's not. I shouldn't say it's not cooling off. I should say the lapse rate is less. The measured or calculated lapse rate is less than adiabatic. So normally,
Following the blue line, and then all of a sudden jumps above it.
right, because here it's adiabatic. Here it's cooled off. It's cooler than adiabatic, so it's.
Any upward
I'm sorry,
bend,
warmer.
Okay, upward bend makes it warmer. Oh, okay.
Because if it was a constant temperature, it would be following this line.
I don't know why the red line doesn't follow the red lines.
The red line doesn't follow what?
Oh. Seriously? The red lines, those are just constant temperature lines.
Okay.
That's not the way anything behaves, that's just there for reference.
All right.
I could remove those and it would be fine.
Okay.
So, that's just so I can say, well, at this altitude, the temperature is -10. But the red lines, which is the temperature line, is going to follow either the blue adiabat, and this is
Or
for
the
a partial.
overlap.
And remember, I guess maybe I need to really make this distinction. There's a difference between what the atmosphere, how it is laid out that day, and a partial trajectory. Because what I'm looking at here are partial trajectories, and then comparing them what the atmosphere is around it when it gets to certain altitudes. Because that depends on, because what the atmosphere around it is depends on what it's going to do from there. If I took this parcel and just forced it up to here, then it would be way cooler than the air around it, and would just plummet right back down.
I guess I've never seen this graph in color, so I can confused on which way to go.
Okay, so at 10 o'clock we've got that little bit of heating. The bottom layer has now mixed up, so it's adiabatic, and this inversion is still stopping the thermals from going any higher.
So you're getting thermals up to 6 there or something.
Yeah, that's the downwind thermal.
Yeah.
That's when you get those
Downwind to
mornings,
base thermal.
mornings where it's real hazy.
Yeah.
Yeah.
So the reason you picked that purple line is because you got there at 10 in the morning and the temperature was 21 degrees.
Well, I'm just assuming there's going to be some variation. So yes, there's the temperature
You
is
still
in-
haven't looked at your actual temperature yet. You're just still theoretical.
right, and I don't need to. I'm never going to look at my actual temperature because this is my. I mean, when you say actual temperature, the actual temperature. If you looked at the actual temperature at a certain spot on the ground, it will. You know, it's not going to go. It's not. If I measure temperature versus time. So, versus temp. Okay. You know, you see predictions that look like that. In reality, it warms up a little bit, and then it's going to leave the ground, and then some cool air is going to come in and replace it, and then it warms up, and cool air comes in and replaces it. So it's not actually that smooth curve. The smooth curve is the average of all the places on the ground. So this is what I'm saying that offset is the difference between what the average temperature is and what the actual temperature is. Because it's not a smooth curve like it's predicted.
It looks like the whole thermal generation process is in those small differences.
Yeah, exactly.
It's caused by
Exactly.
those small differences.
Exactly.
Those,
And then-
1-2 degree differences.
But as it warms up and starts to, so now, say we've got an atmosphere that's mostly cold, then we got one warm place on the ground. So it comes up, it rises up, and now it warmed up the atmosphere a little bit in that range. Okay? And that happens over and over and over, and pretty soon the whole lower layer has an adiabatic distribution. And that's what's happened here. Okay?
Because it will mix until it gets adiabatic.
Right, right. Because it's not just going to be, it's just going to continually mix. Okay. Now, a little bit later in the day, at noon, that low-level inversion has burned off, is what we call it. So the temperature on the ground has increased enough, and this area has mixed so that now that whole thing has moved over. And now we've got an adiabatic atmosphere from the surface all the way up to 14,000 feet. Okay? The dew point is not quite hitting there. Not quite. Again, there's always going to be some variation. So, at this location it's dry. Over here somebody watered their lawn. So there's the dew point may be over here a little bit. In that case, there's going to be a cloud there because it's going to hit. If it's a little drier, definitely no cloud. So if I saw sounding like this would tell me, yeah, it's not saying that at this exact location there's going to be a cloud, but somewhere there's going to be enough variation in moisture that there's going to be some scattered little puffs. Okay? So that's at noon, and once it was here and then it had the inversion here. Once it gets past that low-level inversion, I would say that this would be the trigger temperature for that day. So about 23, 24. If I saw this sounding in the morning, then I saw that sounding in the morning, then I could just draw this adiabat down here and say, yeah, 24, 25 is when it's going to suddenly go up to there. And that would be if I was going to predict a trigger temperature, that would be it. And that would be when I would look at the actual temperature to know when to go flying. Okay, so there's noon, now 1 o'clock, or 2 o'clock. So at this point, again, this line has just kept marching off to the right as it gets warmer and warmer and the boundary layer, the mixing layer gets warmed up. So now if I have a little bit warmer air on the ground, it's going to go all the way up to here. It is going to hit the dew point. The dew point are going to meet. So I get condensation, going to follow the wet adiabat up from there, and then it's going to hit the surrounding temperature there, so it's going to stop. Get some nice little puffy clouds. Okay?
So we just kind of assume the dew point's the same all day long, and the wet adiabatic lapse rate really doesn't change, it's just the dry one, just the temperature related changes, right? And of course, obviously a front or something will throw that all out, but in the morning when you plot this out.
Well, the thing about this is you can get these forecasts throughout the day, so you can see what the models are saying, how the moisture is going to change throughout the day, if there's some mid-level moisture coming in. So you don't have to do... I think a lot of the confusion about soundings, about the forecast soundings and how to use them, is a holdover from people who used to use the measured soundings and had to do a lot of manipulation to those to get to what this is just telling you.
So if you were actually looking at these over a several hour period and there's more moist air kind of coming in, you'd see that. You might see the blue line changing and shifting and the bottom moving over and stuff.
Right. And now that I think about it, I think part of the confusion here is I probably did make a mistake in making this graph. I think this line would start moving over here, so that you would get almost adiabatic, or excuse me, a normal dew point lapse rate because of that mixing. I'm gonna have to change all these now.
Because it's just an effect of the mixing of the atmosphere.
Right.
So with the forecast soundings, when can you get, these, every 2 hours throughout the day before or the morning?
The day before.
The day before.
Yeah, there's some sites you can get 2 days before. And as soon as we're done here, I'm gonna go on the web and I'll
Okay.
show you something. Okay. So here's 2 o'clock, 4 o'clock. So 4 o'clock, again, we've warmed up even more. We got taller clouds. 6 o'clock, temperature's warmed up even a little bit more, and now you can see that the temperature managed to get around that mid-level inversion. So where it was bumping into it earlier, because it's moved over here even further, and we've got the energy from the moisture condensing helping it get around that corner. So all of a sudden the clouds go from this high up to there. So they get taller. Still a wonderful day.
And that's following the wet adiabatic line, that curve, orange curve, right?
Yeah.
Yes. Okay, now we start to get in the evening, sun goes down, you get radiant cooling, and poof, all of a sudden the thermals are going to stop. Now, if for some reason there's a point on the ground that still is at 28 degrees, Starbucks, then there may be one thermal there. If there's some rocks that have been really heated up and now are radiating out heat and keeping the air around them warm, that could still be working. So there could still be places that are working, but for the most part, day's over. Okay. Before we go on, are we getting there? Okay. Okay. So, trigger temperature. So let's say I do have a sounding that looks like this. Then I know that, when do I want to go fly? Do I want to take off at, I don't want to take off when the sounding looks like this. I know that if I have this adiabatic range up in here, that the temperature on the ground needs to get to 25, 23 before I take off. So I'll be looking at the thermometer, and when the thermometer hits 75, I'll know it's time to go fly. So, and I can see the same thing if I just looked at this throughout the, an hourly forecast. It would, when the temperature got there, I would know. Okay. So that would be, until the temperature gets here, really, really weak thermals, not going very high. Once the temperature goes there, all of a sudden, whoop, all the way up to 14,000 feet.
This is primarily at Minden. If you were in Atlanta, where it's high humidity all the time, would it still be the same philosophy?
Oh yeah.
It would be.
Yeah. It's just that
That'll be
this
below.
and this will be really close together, and therefore cloud base will go really low.
Okay.
And because there's so much moisture here, as it goes up, gives up a lot of heat, causes it to keep on rising, and I'm guessing you get thunderstorms. I grew up in Oklahoma, so I know you get them.
What's the, is there anybody done any figuring that when the trigger temperature happens, how much time until the clouds start forming? How long does it take? Are you talking a half hour, 45 minutes, 10 minutes, an hour before the first clouds start forming?
Well, it just depends when the temperature left, or when the temperature dew point crossed.
Well, you gotta start that parcel up, so it's gotta
Yeah.
take a while to get up to.
Well, you know how high it's, if it's climbing at 500 feet a minute or 1,000 feet per minute,
Yeah, so,
and if you know that the dew point and the temperature are a certain distance apart, then you can figure out where cloud base is going to be.
so if you
So
gotta.
the cloud base is going to be 5,000 feet above the ground, and the thermals, you're expecting to climb at 500 feet a minute. You just calculate how long it's just a few minutes.
Okay.
Yeah, we always tell people that the air that's in that cloud was on the ground a few minutes ago. It hasn't been up there that long. Okay, so there's the trigger temperature I can figure out. Now, if I have a day when my sounding looks like this in the morning, I know that as it heats up, this is how, through the day, this is how it's going to climb. Okay. So the thermals are slowly going to increase in height throughout the day. So if I take off, say this is the the 10 o'clock, 12 o'clock, 2 o'clock, 4 o'clock, if I take off at 10 o'clock, I will have only gained a couple thousand feet in 2 hours. I will be very tired and cranky. And I won't have covered much distance if I was trying to go cross country. So I'd probably just wait until the temperature got a little higher before I'd even try anything. So this is a day with a very slow trigger because the lower atmosphere is warmer than adiabatic. If I had a day like this, then I know as soon as that temperature went a little bit further over, the thermals go from this height all the way up to there. So if I was really wanting to do a long cross country on a day that looked like this in the morning, I wouldn't mind getting a little earlier start so that as soon as that hit, I could hang on, until the temperature got to here, and then all of a sudden I'd be up and gone. And it would be a very fast change from I'm at 6,000, I'm at 6,000, I'm at 6,000, and then all of a sudden 5 knotter up to 12,000. Okay. Okay, so if I got a day like this, where if this was the morning sounding, I'm expecting really high temperature, should be a really strong thermals, and I've got really light winds, should be big, strong thermals. So I like this day. If this wind was low up to 10,000 feet and then cranked over here.
What?
Huh?
And you'll have weight?
No, if it was pretty calm up to here and then cranked over. In that case, the thermals are going to get trashed at 10,000 feet. They're going to get sheared apart. Mm-hmm. So I can, by looking at what the wind distribution is, as long as it's calm, I'm good. But if you get a big shear or just have a strong wind, then thermals can be much harder to work.
But like you said, it might be an indication that there might be weight. You might be able to thermal up into waves.
Most likely not if you have instability up to 15,000
Oh, I
feet. Because you got to have that stable atmosphere to get wave. Okay, now if I have a sounding that looks like this, that's great. I got adiabatic all the way up to 14,000 feet, so I should be getting lift up there. Clouds probably forming around here. I don't like that. Because that means that the temperature and the dew point are almost the same. I've got about 35 knots of wind at that level with a little bit of shear. That means there's going to be a little bit of rolling over the atmosphere, which means some of the air is going up, and where it's going up, it's cooling off a little bit. So if this chunk goes up a little bit, and that goes there, then right there I get cirrus, just because those 2 points come together from the change in altitude. Of course, it's way below freezing up there. We're talking negative 25, 30 degrees. So we've got ice crystals, and that just stuff's going to hang around. So the problem is I won't get the big variations because of the bright sunlight. I won't get the strong thermals. If I see a day that, say it started out with this blue line way over here, and then by 2 o'clock in the afternoon, it's saying that, I don't want to be too far away from home at 2 o'clock in the afternoon, because that may shut down my engine.